So in the next homework, we're going to be focused on second order linear differential equations that have constant coefficients. And to develop the solution process for these types of differential equations, we first need to develop the idea of the characteristic polynomial. So to do that, we're actually going to start with first order linear differential equations. And we're going to look at what solution we would get for this if we tried to solve it. So our technique for solving this would be to divide by a. We're assuming a can't be 0, or we wouldn't have a first order differential equation. So a can't be 0. We divide by a, and we wind up getting y prime plus b over a times y equaling 0. And then our technique when we get it into this form is to calculate the integrating factors. So what we did is we took u equals e to the antiderivative of the p of x term. So in this case our p of x would equal b over a. So we took the antiderivative of the p of x term, which is just the constant b divided by a, and we integrated with respect to x, and we wanted any antiderivative of this. So one antiderivative of b over a dx is just b over a times x. And then our technique was to multiply both sides by the integrating factor. And when we did that, we recognized that what we got on the left-hand side was the integrating factor times y prime. And then to solve this, we just integrated both sides with respect to x. When we integrated the derivative, we just got the e to the b over ax times y, and this is wound up being equal to some constant of integration. And then we can multiply both sides by the reciprocal of e to the b over ax, and we wind up getting a solution that looks like a constant of integration times e to the negative b over ax. And the negative b over a is just a constant. It's just some real number. So we can give it a name. We can say let r be negative b over a. And if we did that, then our solution would look like e to the rx, where c is just a constant of integration. And the big idea is that solutions will have the form e to the rx. And so what we want to do with second order, so here I have a second order linear differential equation with constant coefficients. And we're working with the homogeneous case. That's the big idea here, and I should have mentioned that in the previous video. We want to work with a solution to a first order linear differential equation with constant coefficients, but we also want it to be homogeneous. So we're going to work with a homogeneous differential equation. So in this case, we're letting a, b, and c just be any real number you want, but we know a can't be 0, so we need an interval over which a doesn't become 0, because when a is 0, we have a couple issues that happen. One, we wouldn't have a second order differential equation at that moment. Two, a lot of solution processes involve dividing by that leading coefficient, so we don't want the leading coefficient to be 0. And what we want to do is say, hey, look, the first order linear differential equation with constant coefficients had a solution that looked like e to the rx. So let's ask the question, does a second order linear differential equation have a solution of the same form? And so we know what to do to check that. We say, hey, here's my differential equation. If something of the form e to the rx is a solution, we need to plug in e to the rx, the derivative of it, and the second derivative of it, and it needs to evaluate to 0, or we don't have a solution. So the derivative of e to the rx is re to the rx, and the second derivative is going to be r squared e to the rx, and we just plug those pieces in. So we get a times y double prime, but y double prime would be r squared e to the rx, plus b times y prime, but y prime would just be r e to the rx, plus c times y, but we're guessing that y has the form e to the rx, and this would need to equal 0. So what we want to recognize is that each of the three terms have an e to the rx term in it, which means we can factor e to the rx out, which would leave behind ar squared plus br plus c. And the only way for this to equal 0 by the zero product property is for one of those two pieces, one of those two factors to equal 0. But e to the rx will never equal 0 for any choice of r. So the only way for this to equal 0 is for ar squared plus br plus c to equal 0. And this is just a second degree polynomial in R, and we know from our background in college algebra that this always factors. We either, in fact, it always has roots. There are always two values of R that will zero this out. So we either get two real number values for R, R1 and R2, where R1 doesn't equal R2. In other words, we get two distinct real roots. And remember, what we actually calculated the discriminant in our college algebra courses to determine whether we had two real solutions, one repeated root or one solution, or two complex solutions. We always looked at whether the discriminant was not equal to 0, was equal to 0, or was a positive number. Was it 0? Was it negative? And that determined whether we got two real solutions, a repeated solution, so we get a repeated root, or we get two complex numbers. We get R1, R2 are complex numbers that aren't real numbers, because every real number is a complex number, but they occurred in conjugate pairs. So we're R1, R2 are conjugate, non-real complex numbers. So this is what we call the characteristic polynomial. If e to the rx is a solution, and it is, because this equation does equal 0 when we plug in e to the rx in its first and second derivatives, as long as we select the roots of the characteristic polynomial. So this is our characteristic polynomial here, characteristic polynomial or characteristic equation or auxiliary equation, depending on the textbook. And so the solutions to the differential equation are going to be dependent on whether we get two real roots that aren't the same, whether we get two repeated roots, or whether we get two complex roots. So there are going to be three cases. So in the next three videos, what we're going to do is come up with the solution process when the characteristic polynomial has two real roots that aren't the same. We'll then do a second video that says here's the solution process when the roots are equal to each other, we have repeated real roots. And then what do we do when we have complex roots that occur in conjugate pairs? And then we'll do three additional videos where we do worked examples, one for each of the three possible cases.